the basic properties of the Schwarzschild geometry, we introduced penrose diagrams, which are an extremely useful technique in making these sort of general arguments without having to work out all the details of the geometry. So then I and by the way, if those are important, so if it wasn't clear, please ask me, offline, and there is a homework problem where if you work out that homework problem, then I promise you'll understand penrose diagrams at the end of it. So then we turned to talking about quantum field theory. There was, it's always a confusing subject if you haven't heard it before. So let me just, again, very briefly say what the idea was, right? So we had some Hilbert space. It was a tensor product of a bunch of degrees of freedom, say a few at each point in space. And then out of that, we built a field operator. So I guess to try and make people happy, this time I'm going to try and consistently write the field operator as capital phi, and then which is an operator which is a function of space. And then that operator will act on states which are labeled by classical field configurations, which I'll call little phi, with the property that this operator acting on that state gives the classical field configuration evaluated at x. Okay. So that's the basic structure of the Hilbert space. We then argued that the way that we usually like to describe these things to sort of describe quantum field theories is in terms of the vacuum expectation values of these fields, or more generally of their Heisenberg evolutions. And I quoted for you a particular two-point function yesterday of two fields at space-like separation. So the 0 here is the time coordinate, which is taken to be 0 for both. And we found that that wasn't 0. We also, I didn't say it, but I could have also told you yesterday, and I should have, that if you just compute the one-point function of one of these fields, then that is 0. Okay? So then this really is the correlation function of these two variables. And you see that they're non-trivially correlated. And I claim that that was illustrating entanglement in the quantum field theory vacuum. That you can have correlation in a pure state is, of course, a property of entanglement. But I thought I would just briefly give an example sort of to make some of the computer scientists happier. So I'll give a qubit example where you see this same structure, just for you to have in the back of your mind. Okay, what's our favorite state when we're talking about qubits? So I'm just going to talk about 2 qubits. And of course, everyone's favorite state is 0, 0 plus 1, 1. Okay. So, so this is an entangled state. And I guess one way that people say that is, you can compute the von Neumann entropy for the reduced density matrix on one of the subsystems, and you find that it's non-zero. But you can actually also describe the entanglement of this state in this kind of language. So what you can do is you can define the set of Pauli operators acting on the first qubit, and the set acting on the second, and then you can look at their expectation values. So in particular, just for simplicity, I'll focus on the x operators. If you look at the one-point functions, those are 0. But if you look at a two-point function, like say x1, x2, that's 1. Okay, so this is the same structure of the correlation function that you saw in quantum field theory, and you can just think of the 2 qubits as being like 2 different points in space-time. I guess this is a space-time with only 2 points. You can think of the x operators as being like the local field. So x1 acting on the first qubit is like phi of x, and x2 acting on the second qubit is like phi of y. Okay, so this is just a different way of describing entanglement that's more natural in field theory. I mean, for example, you could have checked, had I chosen a product state here, then you would have found that there was no correlation. Okay, yeah.
If I plug in the first formula in the first line,
No, but these states are different, though. So this state is a state which is labeled by a definite field configuration. This state is the ground state of the Hamiltonian, okay?
The upper one is not for any state, it's only for the state.
Yeah, this is the usual thing in quantum mechanics. So these particular bases are an eigenbasis of this operator. And the vacuum is definitely not an eigenstate of the phi operator. And actually, in the homework, you'll work out the wave functional for the vacuum, which actually Rob wrote down in his talk, of the vacuum state in this basis. So in the homework, you'll explicitly compute that in two different ways. Okay, and if you do that, then I think it's impossible to do that calculation and not understand quantum field theory. So that's why I wanted to put it on the homework. Okay. Good. So yeah, these are okay. So let's just be clear that this below the line is a different system than above the line. So x1 and x2 are the Pauli x operators acting on the first qubit and the second qubit, respectively. Okay. So hopefully this helps with intuition. If it doesn't, then you can forget about it. Okay. Good. So now what I'd like to do is try and make this entanglement structure of the vacuum more explicit by introducing what's called the Rindler decomposition. So the goal of the Rindler decomposition is to produce in quantum field theory an expression for the state which is kind of like this one. Right? In this one, sort of, if you see this, you say, of course that's entangled. I see how much it's entangled. You know, I see what the, I can easily see what the reduced density matrix is. Currently, if you haven't seen it before, that's probably not so obvious to you in quantum field theory. If I just, pick some subregion, you may not immediately, say, oh, here's what the spectrum of the entanglement Hamiltonian is, the spectrum. Well, I can call it that, but the spectrum of the reduced density matrix. Let's try and do something more explicit in quantum field theory. So the idea is you pick a coordinate, pick a spatial coordinate. Okay, and the obvious one, let's call it x. Okay, and then break. I don't know what to say. Decompose. Let's say split the space at x equals 0. Okay, so in 4 dimensions, x equals 0 is a 3-dimensional surface. But since we're trying to describe the state, we're going to just work in a given spatial slice. So then x equals 0 just breaks it into sort of two sort of cubes, if you like, infinite cubes. And then we're going to try and describe the entanglement. So let's say this is x equals 0. We'll try and describe the entanglement between the region to the left and the region to the right. Now this is the picture in the spatial slice. But the picture which is actually much more convenient to draw is the picture in the xt plane. Okay, so here I'm interested in the state on this spatial slice here at t equals 0, and then I'm just decomposing the Hilbert space here. Now, once I've done that, though, before I'm able to give you an expression for the state like this, I need to pick some kind of basis of states for the field configuration, really for the Hilbert space on this side, and the Hilbert space on this side. And so here, now this may be a little bit uncomfortable for some of you, I'm not sure, but it turns out that the thing you really want to use. So whenever we give a basis, what do? We pick some operator, and then we use its eigenstates to decompose things. And it turns out the one that you really want to use is the boost operator, the Minkowski sort of relativistic boost operator that rotates you like this in the plane. Okay, so let's draw that out a little bit. So this, it's convenient to draw these light cones again. So then what the boost operator does, right, it takes a point here, and it does that to it. It takes a similar point here, and it does that, where this is eventually going to asymptote. And then if you think about what it does to the whole, let's see, what it does to this whole line here, it rotates it like that. Or then if we do the inverse boost operator, like that. Okay? So you can see that the action of the boost operator is sort of confined to this wedge in a nice way, or similarly this wedge. And then actually if you look in these wedges, the top and the bottom, then right, these points are doing something like that. And these points are doing, well, again, I'm not good at drawing 45-degree lines, but they're doing something like that. Okay, so the picture looks a little busy, but, oh, sorry, yeah, you're right, it's the other way. Yeah, like that. So this decomposition, where I take ordinary Minkowski space, I look at the tx plane, where I just pick some x, and then I split it into these 4 wedges, is called the Rindler decomposition. This right wedge is the right Rindler wedge, the left one is the left Rindler wedge, and then this, I guess we can call the future and the past Rindler wedges. Okay. Now, what I'd like to do then is, so in particular, there will be, if I cut the Hilbert space here and I look at the states in this wedge, there will be states which are eigenvectors of the boost operator, okay, which I can label by their eigenvalue, and similarly on this side. Okay, so now I'm going to introduce something which no one in the school has talked about yet, but it's something which I feel like, as a matter of principle, needs to appear at least once, and that's the Euclidean path integral. So why am I doing something like that? Well, I need some way to pick out the ground state here, okay? And there's a sort of generic way in any quantum system of finding the ground state, which is that you just take some state, your favorite state, chi, which is probably not the ground state unless you're very smart, and then you act on it with e to the minus th, where t is large. Okay. Now, if you do this, well, what's going to happen? You expand this state in terms of the energy eigenstates, and whichever one is the one that has the lowest energy is going to be the one which dominates the sum once you've acted for a long enough t. Now, there's some subtlety there about whether or not the system has a gap. But let's just say that even when it has a gap, it's fine. But you have to think a little bit harder to make sure that you really get the ground state in the way that you want. But this isn't quite the whole thing. So now I can project this onto some basis that I like, say the phi basis. Then to get the normalized ground state, I have to divide by the projection of chi onto the ground state, right? Because I insert a complete set of energy eigenstates here. The ground state will have this coefficient. And then I take the limit as t goes to infinity, okay? And this is a formula for the ground state wave function. Yeah, so with gapless systems, like I said, you have to think harder. I don't know what this is doing there. I think it's still true. Yeah. I mean, sometimes you have to make sure that you're computing what we would call an IR safe quantity. So usually in a gapless system, the ground state wave function is kind of, it might not necessarily be something that you really want to talk about. But then what you can do is you can use this expression and then put into it, the expectation values of things that you're interested in. And then usually I think the limit works out okay.
In other words, it's not literally true.
Yeah, in that case, it's not literally true, but it's sort of formally true.
There can be arbitrarily soft stuff.
That's correct. Yeah, no, that's correct. But you can, for now, let's just imagine that there's a gap, and then it's fine.
But even then, chi have to be, if it has chi has a different symmetry than the ground state.
Yeah. So you notice I divided by this. So this overlap has to not be 0. So you have to, if you make a really bad choice, then you're in trouble. But I mean, if you just choose chi randomly, it's going to have some overlap with the ground state, and that's all you need. Okay. So why did I write this? Well, so if I'd put an I here, then you would have thought that I was just evolving for a long time. And then we know that, well, what do path integrals do? Well, ordinary Lorentzian path integrals, you give some classical field configuration here. You evolve for some Lorentzian time, and then you project onto some other classical field configuration. You do the Feynman path integral over this. So that's something like, so now maybe I'll write phi hat to indicate that these are spatial configurations. This is a space-time configuration that you're integrating over because you're summing over the entire history. With the action, but then you pick the boundary conditions to be that sort of, phi hat of 0 and x equals phi of x, and then phi hat of t and x equals phi prime of x. Okay, and this integral. Okay, so this is the picture. This is the integral that the picture is representing, and then what Feynman showed is that this is just equal to evolving for time t. Okay, and so this is the propagator, if you like, of the system. Okay, so this is Feynman's formulation of quantum mechanics, and you see we're almost doing it, right? If I put an I here, then we would have been in great shape, and we would have had a path integral expression for the ground state. But that's actually easily corrected. All you need to do is analytically continue t to imaginary values. So I mean, the details of that are of course important when you really want to try and do these calculations. But I think it's easiest for us to just say we pick this to be minus I tau. Okay, and then I do the path integral with the time coordinate being imaginary, and that then is exactly computing this. Okay, so if I do that, then the only thing that gets modified in this formula. So I had the action here previously, but then I just get still an integral over histories with the same boundary conditions as before. But now what appears here is the Euclidean action instead of the Lorentzian action. And the Euclidean action is related to the Lorentzian action by just plugging this in everywhere. Okay.
So maybe you should use capital T instead of tau.
I think I'd actually rather do this. Okay. Let's see. So So why did I introduce this? Well, as usual, the only reason I ever introduce anything is because then it allows me to do the calculations I want by picture instead of by actually doing the calculations. And this is actually one of the classic examples of that. So now, in order to get the ground state, what I want to do is now this will be the Euclidean time. This will be x. So now there's going to be a field configuration here on the right side. There's going to be a field configuration here on the left side. So now I've just taken the tensor decomposition. So now instead of labeling it by one phi, I'm labeling it by the fields on the left and the fields on the right. And then I just want to do the path integral, the Euclidean path integral, over this whole region here. Okay? And if I do it over this whole region all the way down to minus infinity, then that will be computing this. And then I won't quite have the ground state wave function because there's this normalization issue. But this will be proportional to phi left, phi right, the projection of the ground state onto phi left and phi right. Okay. And actually, in the homework, I have you. So I'd already said that I had you compute this one way. I also have you compute it this way. Just so that, again, if you want to understand this, nothing is better than computing it in an example, and then everything should be clear. And of course, the homework is optional if you don't want to compute it. Yeah.
So here we have to put a lot of some kind of boundary condition which can be possibly arbitrary. How do we deal with that?
At infinity, you mean?
Yeah,
Yeah, so the thing is, you see here, right, so in this, the details of chi don't matter, it just matters that it has an overlap. So the simplest thing to do is you just say that at some very early time, all the fields are 0. That's the simplest thing to do. That's what I have you do in the homework. And then, or maybe another way you can say it is you just say the fields go to 0 as t goes to minus infinity, and that gives you some boundary condition. Yeah. Okay.
I have a completely off-the-wall comment, which is that formula on the upper left is also the formula that I teach in another guise as the page rank.
Okay.
Where the time evolution is instead the Markovian process of walking over the web, and the projection on the ground state is the steady-state probability distribution.
Yeah.
And it projects out for the same reason you're projecting out to the eigenvector.
Yeah, exactly. Yeah, I guess if you do quantitative finance, you like this kind of formula too. So, after we all can't get jobs, then we're going to see lots of this formula.
Can I ask?
Yeah.
So you obtain this
Yeah.
inequality. What you obtain when you integrate out, or is it already decomposed and integrate out, and you find a vacuum?
Yeah. So I'm integrating over all the fields in this blue region.
It is decomposed before you integrate out.
Well, you can do it either way. So I fix the field configuration here, and I do the integral. It's just that I've happened to have chosen the field configuration to split it into the left and the right for reasons that we're about to see. But it's the I mean it's not necessary to write that. I mean once we have the ground state wave function, we can then do the decomposition.
Okay, but this decomposition is not the result of the integration.
No, definitely not. It's a choice. Yeah. Okay. So let's see. All right. So okay. So why did I bother, and in particular, why was I talking about the boost operator before? Well, the thing is, so what you're going to do on the homework is you're going to do this path integral along slices like that, okay? But there's nothing to stop me from doing the path integral on slices like this instead, in angular directions. Okay. So and in that case, it's kind of like phi r is say the final state, and then phi left is the initial state, okay? But where instead of using the Hamiltonian to do the evolution, I'm using the operator which generates rotations in the Euclidean plane, in the plane of tau and x. Okay, yeah.
Also have to do this adiabatic is the king of your Hamiltonian there in that formula.
Well, yeah, in the formula I covered up. Yeah. Yeah. So you have to. So this tau going to infinity here is important. I mean, that's So that's all you need, right? I mean. So again, for this to be rigorously true, there's a gap in the Hamiltonian. As long as there's a gap, I think you're happy, probably, right? Because then it's just sort of clear that this works. By just inserting a complete set of energy eigenstates, and and you still have to do it for a long time, but that's the only restriction. Yeah. Okay, so I can split things up like this, and what does that mean? Well, what it means is so these slices I drew in white, I can also think of as here's phi right, and here's something I'll call theta times phi left, which I'll comment on in a sec. And then the lines just become like this. Except that I'm now evolving for pi. But I'm evolving for pi in this direction. And maybe, where did the blue go? I'll shade this in. So that this whole blue region before is now mapped just to the region in between these two guys. Okay, so I just unwrapped this, nothing deep. So okay, that's fun. What? Well, yeah. If you like, yeah. So yeah, this way it ends, and this way it sort of goes on forever. Or maybe I should flip it. And I think that's right. Okay.
Sorry, what do you mean phi L? Should that final state just be phi L, and then the intermediate state's like a linear combination?
Yeah. So phi right is this half here. So it's some field configuration for the right Rindler wedge. So that's what's on top now. Phi left was the field configuration for the left Rindler wedge that I had here. And then this theta, so this theta is called CPT, and it's something that exists in any relativistic quantum field theory. The only thing you need to know about is it's the operation which takes a state here and flips it over. Okay? And so then when I did this, I kind of had to flip it over. So I had to put in that theta. Okay. And then I just integrate over the fields in this blue region with these boundary conditions, and that computes for me this. Okay? But the good news is that I know how to compute this in a different way, which is that if you look at, let's see, where did I put it? Oh no, it's here. So remember we said that in Lorentzian time, the boost operator does this, okay? But if we go to Euclidean time, then the boost operator, which is sort of a pseudo rotation when t is real, becomes exactly this rotation operator when tau is real. The easiest way to do that is you just look at how the boost acts on t and x, and then you analytically continue that formula in t, and you find that it's exactly this, okay? Which means that what this has to be equal to is that I take theta phi left, I act with e to the minus pi k, where k is the boost operator, and then I project onto phi right. Okay. So let's see. I think what I'll do now is, so let's just say a little bit more explicitly what that is. Well, okay, so whenever you see a formula like this, the thing that you obviously want to do is you want to insert a complete set of eigenstates of k. Okay, and then you can just evaluate this trivially. So indeed, what? K is the boost operator. So it's the operator which, so in any relativistic quantum field theory, well, in any relativistic theory at all, you have a boost operator, which is the operator that implements this boost. And yeah, and so like I said, the point is just that if I put an I here, that would have been the boost operator in Lorentzian signature, but since I didn't put the I, it's the boost operator in Euclidean signature, but that just rotates in the Euclidean t and x plane. Yeah.
I thought you had to do the path integral over all elements of the boost operator, rather than just calculating that single element.
Well, I don't integrate over the boost operator. I integrate over fields, over field histories. And it just so happens that this integral, where I integrate over all fields here, and remember I'm just integrating e to the minus se, the Euclidean action. I'm integrating it over all field configurations here, with the boundary conditions that up here I get phi right, and down here I get theta times phi left. Okay, so that's just that's some function of phi left and phi right, and from this presentation, you can see that it has to be this function of phi left and phi right. Okay, now we're almost there. Well, it's from special relativity, right? So it's the thing that changes your coordinate frame from.
I mean, I know what boost is, but I cannot write it as an operator on the field because.
Oh, you're asking for an.
Usually defined on a slice, time slice, right?
Yeah, the boost operator is defined on a time slice. So okay, I'll get the signs wrong. I can attempt to write it for you, but
Are you going to define Rindler time?
Yeah, I'm going to.
You could just postpone the question till then.
Well, yeah, but I think he wants an expression in terms of fields. But yeah. I mean, John is right, but let me just try briefly to make you happy. I may or may not succeed.
Just to understand that, so boost
Yeah, yeah.
Good, and then I not see how it's an operator then. But not in terms of some
So in any quantum field theory, so consider any relativistic quantum field theory. You have a set of operators whose algebra is the Poincare algebra. This includes the Hamiltonian, it includes momentum, it includes rotations, and it includes boosts. Every one of those is a generator of the symmetry and therefore must be realized by a linear Hermitian operator on the Hilbert space. Okay, I'm just picking the Hermitian operator which realizes the boost symmetry.
But xdt plus tdx.
Well, yeah. So that's its action on the right. Its action on the coordinates. The generator of boosts, just from the point of view of coordinates, is this killing vector. I don't know if that helps. Maybe it helps some of you. But there's some expression for that. I mean, since it's an operator acting on the Hilbert space that I defined before, there must be some expression for it in terms of phi and pi. The expression is something like integral d cubed x of x times the Hamiltonian density plus t times the total momentum. Okay, I think the signs are probably wrong, but roughly that's what the boost operator is. But it doesn't matter actually what the details of what it is. It just matters that it exists, and that follows from the existence of Poincare symmetry, or from special relativity. Okay, great. So now we're doing well. So what does this tell us? Well, so I won't go through all the steps, but you insert a complete set of k, both here and here, and then you have to use the special properties of CPT to flip the theta back to the other, to the phi left back to the other side. And what you find then is that this is equal, or actually let's just say proportional, to a sum over I, e to the minus pi omega I, phi left, I star, left, phi right, I right. So I just have to, now I've defined everything except for this I and this I star, but these are just the eigenstates of the boost operator on the two sides. So k acting on I right is omega I right. And then I star left is just this CPT operator acting on I right. So the CPT operator is the thing which sort of, it flips you around like that. So it brings you, it gives you a map between the left and the right. So I wouldn't actually even worry too much about the star. It's important if you actually care about the details of this. But so anyway, so this is great because now what we've learned is that the Minkowski vacuum as a state just looks like this, okay? And that's what we wanted. Just one section more. So as you can see, now I've decomposed the Hilbert space into the right and the left, and I've written out the ground state explicitly as an entangled state between the right and the left, where there's some weights here, which come from the eigenvalues of the boost operator on these eigenstates of the boost operator. Yeah.
What will happen if you put 2 pi instead of pi?
Well, yeah. So then you get the wrong answer, right? Because it was important that it was pi to go around just halfway. If you put 2 pi, you'd go around all the way, and then you wouldn't be computing the wave function. You'd be computing something else. I mean, you'll see actually pretty soon, essentially what you would be computing. But
This expression is true up to normalization.
yeah. Sorry, that's right. I was being lazy. So yeah, there's let's say that there's some normalization factor, which I'll call 1 over square root of z. Okay. So yeah, I get this may be unfamiliar, but these are sort of very fun and useful methods. So I wanted to present them. So yeah, that's what I'm about to say. So now what we want to do. So there's an interesting observation to make here, though, which is that here I computed the pure state of the two wedges separately. But you can actually, of course, also compute the density matrix just for one wedge or the other. So maybe I'll just write that here. So now that I have this, it's a moment's effort to trace out, say, the left side and just get the right side. And what you find is that the density matrix is 1 over z. Let's see, 2 pi omega I. Okay? And this is a density matrix I guess we all like. This is the canonical density matrix of the thermal distribution. This is the Boltzmann, I don't know what you want to call it, the thermal density matrix. If you make the identification that the temperature is 1 over 2 pi. Okay. Now, you may ask why the temperature is dimensionless, and I'll comment on that a little bit later in the talk. So this is the upshot, though, is that if you look at the Minkowski vacuum, you trace out one side, you're left with a thermal density matrix. But it's a thermal density matrix where the energies, the H that appears in the exponent is not actually H, it's K. It's the boost operator. Okay. All right. So that's sort of the general discussion of Rindler space. Now I'm actually also going to. What?
What looks like tau is actually pi.
Where? Let's see. Oh, this is pi. This is pi. Yeah, it's in 3.14159. Yeah. Okay.
Yeah, how we construct the mixed state from the beginning we dealing with the pure state. How can we construct the mixed state?
No, I just did the partial trace. I traced out the left side. So anytime I have a bipartite Hilbert space, I can always trace out one of the parts, and that gives me a density matrix on the other part. And that's all I did. So if
Specific mixed states.
yeah, it's this mixed state.
But what's the meaning of this mixed state?
Well, I'm not sure what to say. I mean, if you lived in the right wedge and you never left the right wedge, then you wouldn't care what was going on in the left wedge, so you'd throw out that information. And then you'd think that just for experiments in the right wedge, you can just use the density matrix, which is this density matrix. And you can predict the result of any experiments that you do in the right wedge. Yeah. Yeah, that's correct. So essentially, so remember the phi of x was not really just one operator; it was a bunch of operators because it's labeled by this x. Okay. So and the phi's at different x's commute. That's what we talked about before. So you can think about them as just a set of independent operators which act on different tensor factors in the Hilbert space. So then I just chose to split this set of operators into two parts. There's the parts with operators with x greater than 0 and the operators with x less than 0. The ones with x greater than 0 I call phi right, and the ones with with x less than 0 I call phi left. Yeah. So can you just speak up a little?
Is there any intuition why we end up with this boost eigenbasis?
Well, that was a choice. I just chose to use the boost eigenbasis. Now, I guess it should be clear at this point that the reason I chose it was because then you get this nice thermal density matrix. Now, they also have a physical interpretation, though, which I'm going to get to in a minute. Yeah.
The Rindler observers in the right and left wedges.
What?
The Rindler observer in the right and left wedges, right?
Yeah. So, yeah, that's where we're going now.
That's only true in the case of T being very small, or the temperature being very small.
No, there's...
Pi large enough. I mean, otherwise you don't get
Well,
the...
no, pi is 3.1415926535889.
No, but what I mean is that that you get there, the ground state was only true when you took the time of real.
Oh, sorry. This T, yeah, good. So it's important that this T is not that T. This is a temperature.
No, that's for sure. No, but
Yeah.
I mean, there, when you rub like this omega, this is
Oh.
the ground state.
Oh, no, but yeah, no. This is, in this calculation, the time that I talked about before is infinity because I took the entire lower half plane. So the time that goes on these horizontal slices did evolve for an infinite amount of time, from minus infinity to 0. And I just chose to do the integral in a different order, where I only had to do it from 0 to pi, because I was doing it on these angular slices instead of on these horizontal slices. Yeah. Okay, so maybe one more.
You change a little bit your variables.
Yeah, that's right.
Okay,
Yeah.
that's what I mean.
Yeah.
You put in a couple triangles
Yeah.
Put in a complete set of eigenstates of K.
Yeah.
So these were eigenstates for the bottom half of space?
Yeah. So yeah.
Space is complete in that case.
Well, no. So the space. Remember, the Hilbert space just lives on a time slice. Okay. So then, and then the operators just act on this time slice, and so then there's a complete set of states I can use just to describe states here. Yeah. All right. So I think let's go on. All right.
Is it easy to find these eigenstates for a given field theory?
Well, so in a free theory, I'm about to do it for you.
But an interacting theory?
In an interacting theory, no, not necessarily. But see, but I mean, there's got to be some trouble somewhere, right? I mean, this is true in any quantum field theory. So apparently, it must not be that explicit. Yeah. Okay. All right. So I'm just going to say a little bit about how this works in free field theory to get some more intuition. So. I should say, by the way, you may think that I'm belaboring Rindler space too much, but honestly, working in this field of black holes, something like 4 out of 5 confusions about black holes are resolved by going back to Rindler space and understanding what happens there, as any of the people here who work on black holes can confirm to you. So it's really good to get it right. Damn it. Okay. There we go. I see. Great.
Same as the number of minutes you recommend sugar and Scott.
Oh, yeah? Yeah. Did you learn that on TV? Oh, sorry, Rindler. Yeah, let me just call it the Rindler decomposition. Often this right wedge people call Rindler space, and I may say that sometimes by accident. Yeah, I was trying not to. But. Okay. Okay, so right. So now in free quantum field theory, as we discussed yesterday, the thing that you want to do is you want to take your phi operator, which now I'll put in the time dependence too, which means I took the one without the time dependence and I put in I went to the Heisenberg picture. So then you want to write it as some sum of some classical solutions of the equations of motion, which I called modes, Fn. With creation and annihilation operators for those modes. So Fn star, An dagger. Okay. And then I'm choosing the field to be real, or to be Hermitian, since it's an operator. And that's why the thing that appears here has to be the star of the thing that appears here. And then so in the previous, yesterday we took, it was yesterday, we took the plane waves because we were doing Minkowski space. Here, so what I'm going to do is I'm going to choose a different set of modes, which are more natural from the point of view of the Rindler decomposition. So in order to do that, I'm going to have to inflict on you the last coordinate transformation. I think it may even be the last period. Yeah. So that's it's an unfortunate fact of this business. So I'm good. What I'm going to do is I'm going to reparameterize the x and t. I'm going to reparameterize them by the orbits of the boosts. Okay, so this is kind of the obvious thing to do. So I want to use these hyperboloids to be time. So I'm going to pick coordinates that just live in this wedge, and then where the time kind of evolves like that. Or I guess really these are lines of these hyperboloids are lines of constant distance here. And then where the time is just this is just accomplished by evolving with the boost operator. So clearly, if I'm going to try and make sense out of these boost eigenstates, this is going to be a good thing to do, to find some coordinates that play well with the boost operator. So it so happens that the coordinates that you like, so C is going to be a spatial coordinate. And let's see, okay, how about, I'm going to call it tau r, okay? And I'm going to write the r religiously because this is a Lorentzian coordinate. It's not the Euclidean tau coordinate. So that's this r is there to make that distinction. And t is going to be something like this. Sinh tau r. Okay. So, you know, the details of this don't matter too much. It's just the only thing to remember is that in this picture, the lines of constant xi are these hyperboloids. And the lines of constant tau right are these lines here. Okay? So you know, just, you know, because I know you're all missing it, I'll write down the metric in these coordinates. Okay. So this should look kind of like the formulas that we were throwing around yesterday for the black hole. One difference, though, is that here, when I write y with the vector, I just mean I'm collecting y and z together, and I don't want to keep writing y and z separately. So the thing that appears here, which I'm going to ignore, is now a plane, whereas yesterday it was a two-sphere. And okay, so one good news is from this form of the metric. If you remember, so if I consider, for example, a null curve that's going just in the tau and xi plane and doesn't have any momentum in the y direction, I can cover this up, and then I can use the theorem we talked about yesterday to ignore that, and then it just looks like Minkowski space again. So in these coordinates, the null geodesics again are going to go on 45-degree lines in the xi and tau plane. Okay. So now, okay, I've got these coordinates. So what? Well, now I want to write down some solutions of the wave equation in these coordinates. So, but before I do that, let me just comment that now. So by construction, this tau is exactly the time of the boost operator. So if I can write down configurations which have definite values of the energy, or really the boost energy for tau, then these creation annihilation operators are going to create states of definite boost energy, and that's what we're after, because that's what appeared in the expression for the vacuum. Okay, so then in order to do that, obviously what we want is we want to look for some solutions of the form e to the minus I omega tau right times some function which I guess I called psi omega k, which depends on xi. Okay. So these are just some other. So you know, and then this is going to be constrained by saying that the whole thing obeys the wave equation. Now, more explicitly, what that means is that this psi has to obey some Schrodinger kind of equation. Oh, I forgot an important thing. Times e to the I k dot y. Okay. So this is a solution which looks like a plane wave in the y direction, in the direction that's orthogonal to the tx plane, and it also looks like a plane wave from the point of view of tau r, but then it's going to have some non-trivial dependence on xi. Okay. Equals omega squared psi r omega k. Okay. So, you know, this is some differential equation. Its solutions are Bessel functions, which I'm not going to get into. But I don't need to, because this is the Schrodinger equation, right? Here we have minus ddx squared, where now it's dd psi r squared, plus some potential, which is exponential, times some thing which you can call a wave function, but it's not a wave function here. It's just a solution of some classical equation. And it's equal to some energy, which actually here is the energy squared, times the wave function, which is now the mode. Okay, so I'll often call this a Schrodinger type equation. And of course, the reason why I like that is because now we can just see immediately what the properties of the solutions are going to be. Because I think, well, actually, in this room, it may not even be true. What I usually say here is that solving the one-particle Schrodinger equation is the one thing that everybody knows how to do. But I'll pretend that that's the case. So what's going on here? Well, we've got some exponential potential that's going like this. And so then apparently what's going to happen is that for a fixed energy, we're going to have solutions that oscillate like plane waves here, and then which die exponentially over here. Okay, so that's sort of undergraduate physics. Now I've done something a bit dishonest here. I've plotted both the potential and the solution for the equation on the same y-axis. So forgive me. This is the potential. This is the psi. Okay. So it doesn't really matter too much about these. The upshot to take, though, is that for large negative xi, so yeah, I should say this is xi-r. That at least both plots agree on. This just oscillates like a plane wave. Okay. So this solution psi, it goes to e to the plus or minus I omega xi-r, and then it really just looks like a plane wave. So now where is, I should comment that in this wedge that I drew, xi equals minus infinity is where you're right up against these light cones here, and xi equals plus infinity is when you're way out here. So the moral of the story is that you've got these modes, so these things that we call modes, are confined. They're trapped because there's this exponential potential that suppresses them as you get too far away. Now, so this m squared is the mass, but as this m squared and k get bigger, this potential gets bigger. That's what this says. And then the modes are confined further in to more and more negative xi. Or in other words, they're confined to be closer and closer to this light cone in the Rindler decomposition that I talked about before. Okay?
So this is the boost operator.
Yeah. So the boost operator now I can say is the generator of tau r translations. Or more accurately, that's the action of the boost operator on the right wedge. Yeah, these coordinates are only really covering the right wedge because xi is going to minus infinity and we're still just getting to here. Yeah.
The solutions of the classical solution.
Yeah.
The plane wave solution we have in intuition for.
Uh-huh.
We have a coupled oscillators and we just create plane waves traveling there.
Yeah.
What's the intuition of this?
Well, I'm trying to give it to you. So you have they look like plane waves in here. There's some sort of they're propagating in and out here, but then eventually they get damped and they fall off at large distance.
So this is in terms of psi.
Yeah, in terms of xi, but
how would it look in terms of?
well, so we can look here. So let's look at let's just look at their behavior at tau equals 0. That's the same as t equals 0, and just look at the profile. So then x is just e to the xi. Okay. So then what happens is that this infinite plane wave oscillation here going out to minus xi equals infinity is all cramped into the region, as you're approaching x equals 0 from the right. And then as you go off to the left, and as you go to the right towards large x, which here is large xi, then they oscillate for a while, but then eventually they feel this potential. And then they just get damped exponentially. So they're really confined. You should think of it as being like, now we can get to the punchline, right? So these creation and annihilation operators just work by putting more and more particles into these modes, which are usually called Rindler modes. And since we know, so we're just looking at the right wedge, so we're free to just look at the density matrix on the right wedge, and we know that it's thermal. So what it means is that all of these modes are going to be thermally occupied. So according to these modes, you should think of the ordinary Minkowski vacuum is just that you have all these modes which are confined near here and thermally excited. So there's sort of some thermal gas of particles in here, which is sort of dilutes out as you go out. Okay? Now, of course, the... Well, no. I mean, so remember, so we're looking at tau equals 0 just for intuition. So then, I mean, these are monotonically related, right? I mean, so if x is large, xi is large. Well, Yeah, so it's exponential in Xi. So that I mean that's good. That's what this picture is supposed to say. So if you
That incorrect, because you have exponential in xi, but then x is exponential in xi again.
yeah, so in X the following is some power. Yeah.
I guess for intuition, you could also say that this is a uniformly accelerated.
I'm about to say that. Yeah, yeah. So what does this really mean, right? I mean, what does this, this really mean? It seems so far it seems like I just introduced these funky coordinates, which are not the coordinates you usually like, and then I found that things look kind of funky in those coordinates. Okay, so great. But as John said, there's actually a sense in which these coordinates are very natural. And the sense is that if you look at it, if you look in Minkowski space, not at an inertial observer, somebody just coasting along like this, but you look at somebody who's accelerating with constant proper acceleration, then it turns out that their trajectory ends up looking like that. Okay? And mathematically what that means is that they're sitting in a constant Xi. Okay? So that's what this Xi really means. If you're doing constant acceleration in a relativistic theory, you're just sitting at constant Xi on one of these lines, and your time, the local time in your frame, is this tau. Okay? And then what we've learned is that the ordinary Minkowski vacuum, from the point of view of somebody on one of those kinds of trajectories, looks thermal. The density matrix, in terms of the coordinates that are natural for this accelerating person, is thermal. So this is called the Unruh effect. It's the claim that if you take a real physical detector and you put it on an accelerating trajectory, it actually clicks. And it clicks as if it's in a thermal bath, even though you're in the Minkowski vacuum. So this is a remarkable fact about relativistic quantum field theory. If you end up chasing the units through, and I figured I would just, this will be one of the few cases where I actually write some dimensionful things. So the Unruh temperature ends up being h bar times your acceleration divided by 2 pi times c times k Boltzmann. So this 1 over 2 pi is the 1 over 2 pi that we got before, and now I've just put in the dimensionful factors that I was ignoring before. And you can see two things. One is that if quantum mechanics goes away, so we send h bar to 0, then the temperature goes to 0. And you can also see that if we get rid of relativity, so we send c to infinity, then the temperature also goes to 0. So this is something where you need both quantum mechanics and you need special relativity before you can get this sort of bizarre fact that accelerators, people who are accelerating, at constant acceleration, see a temperature. What? Oh, that's just because people who don't have very much sense like to measure temperature in units of Kelvin instead of energy. So then anytime you talk about a Kelvin, there's always going to be a Boltzmann constant somewhere. Yeah.
So where is the acceleration A encoded in these parameters?
Yeah, that's a good question. Good. So I'm surprised nobody complained about this. I guess now I see that there aren't that many physicists here. So what happened in the units in this equation? So this has units of length. And I'm in a relativistic theory, so this also has units of length. But then the things that I put in here are clearly dimensionless because they appear inside of exponentials and Cauchys and things. So it means that there's some length scale here, which I didn't write. Okay, and if I wanted the Xi and the tau to actually have units of time and length, as they would, in the frame of somebody who's actually accelerating, then I would have to insert a length scale here. Say something like, I don't know, L over L times L, L over L over L. Okay? And then what you would find is that when Xi equals L, so then this L you can work out is how the acceleration gets in, because you look at the trajectories in these coordinates. Okay.
One point, I think it's not accelerating whole space.
No, acceleration is something you can define locally, right? You can just, you can be sitting in your box and you can drop your paper and you can see what happens to it. So, you can really define acceleration just in terms of what's going on here. Yeah.
Is the mass necessary? It doesn't appear in the temperature here. So if you don't the mass to 0, what would happen?
Nothing. It would be the same.
Because it's
Yeah, yeah, same story. Yeah, yeah. Yeah, actually, pretty soon I'm going to take the mass to 0 in general. Okay. Great, so that's Rindler space. I want to make one more comment about it, and then we're going back to black holes. Okay. So, let's see. All right, let's kill the modes. So the final comment was that this entanglement that we've discovered in the Minkowski vacuum is really important, okay? It's essential. It's essential that this is entangled with that. And if it weren't true, then you would be in for a world of pain, literally. So let's try a simple thought experiment. So we found now, right, we found that the Minkowski, we had the Minkowski vacuum. And that induced a thermal density matrix on row right and also on row left. Although I didn't. So I could have had this whole discussion also on row left, and we would have gotten the same result. But in the Minkowski vacuum, the entropy of these density matrices comes from entanglement. But I could instead define a new state. I could define a new row, which is just row left times row right. So this is a state on the full Hilbert space of this t equals 0 slice. But it's a state where the right wedge and the left wedge are completely uncorrelated because I just threw away all of the quantum correlation. I threw away all of the entanglement between the left and the right by just tracing out and then taking the tensor product. Now, this is an interesting state because if you just lived in the right wedge or if you just lived in the left wedge, then this state would be indistinguishable from the Minkowski vacuum because you just wouldn't have access to the degrees of freedom that know that this state is not the vacuum, okay? But say you were to do this. Say you were to go up here. You were to cross the horizon. What would happen? Well, the thing is that this state actually is going to have to be extremely singular. And here's one way of seeing it. In the Hamiltonian, there was a term which was like dx phi squared, okay? Evaluated at x equals 0. So this is a term in the Hamiltonian which compares the field here with the field here. And if they're that different, then it costs you a lot of energy, okay? Then that increases the energy by a lot. So if we're in this kind of state, then the field here is going to be completely uncorrelated with the field here, which means that generically this term is going to be very large, okay? Which means there's got to be a ton of energy in this state. But where's all the energy? We just argued that if you stay out here, there's no energy, so it can't be here. And if you stay out here, it just looks like the vacuum. There's no energy, so the energy can't be here. So it all has to be here, right at this point. Just sitting there waiting for you to discover when you jump across the horizon, okay? So there's something terrible going on up here in this state. And the something terrible is called a firewall. Okay, so this is the canonical example of what people mean when they talk about firewalls in all of the chaos and black hole theory that's going on recently. They mean that the left wedge has lost its correlation with the right wedge, and you can't tell on either side. But because of this, you sure can tell when you go across. Now, okay. You might say I picked an especially extreme example. I chose a product state. But it so happens that actually you really don't need to correlate the two sides very much in order to start having problems. One way you can do that is you can throw detectors across and see if they click or not as you start decorrelating the state. Or in fact, even if the two sides are entangled, but they're just entangled in the wrong way, so you take the vacuum and you act with some unitary transformation here, that's already bad enough. So you really need this specific special entanglement across this point in order for the infalling experience into the future wedge to be smooth. Okay. All right. So now I'm really done with Rindler space, and I can go back to black holes. Yeah.
What corresponds, physically, that's crossing the horizon to?
Yeah, so the thing, it's a little bit, right, so here I'm just talking about ordinary Minkowski space, so it's not really fair to call this a horizon, but it behaves a lot like a horizon from the point of view of somebody who's a constant accelerating observer. So people are often lazy, and we call this the Rindler horizon. But it's just, I mean, this is still ordinary Minkowski space. Here's T, here's X. So, say there's, look at this point right here, okay? In a nanosecond or something, I'm going to cross through its future light cone. So, you do this by just sitting here in an inertial frame and doing that.
Why do you expect to see that? That's not the real wedge, but the ground state.
Oh, yeah, no. So in this case, So in this case, this is not the ground state, so you don't expect to see it, which is fortunate for us. Okay, but we're going to argue later in the context of black holes that there are cases where you might expect to see this, and that's bad. Okay. Sorry, what? Oh, yeah. It's because there's a term in the Hamiltonian that compares the field configuration on these two sides. And so say it were true that we were only interested in field configurations that were smooth here, that had a finite derivative. Then that's correlation between the two sides, right? Because it's saying, whenever this field value is 10, that one's 10 plus or minus epsilon. Okay? But in this product state, there can't be any such correlation. So, typically, this will be 10 and this will be minus 10 or something, in some units. And then this term in the Hamiltonian will be large.
Can you just clarify my thinking really quick? So you said if you were an observer, in Rindler space by definition, you're constantly accelerating.
Yeah.
But then you mentioned if you were to say then,
turn off the rockets.
Yeah, turn off your rockets and cross the horizon, then it's not Rindler space anymore.
Well, that's why I didn't want to use the word Rindler space. The Rindler wedge is a piece of Minkowski space, and you can choose to stay in it or not.
But you need to solve, what the modes are according to this.
That's correct. But I mean, we've essentially done that. So I wasn't too explicit about it. But so we described the boost eigenstates in this wedge, and we can do the same thing over here to describe them in this wedge, and that gives us a Cauchy surface. Once we have that, we can just push the modes forward up into here. Yeah.
So, and the corresponding black hole, would it have an infinite Schwarzschild radius?
No.
Because the acceleration is constant, so this would correspond to a mass which is infinitely far away.
Yeah, so ask your question again in 10 minutes if you're still confused about it, because we're going to start talking about black holes now. Okay. All right. So on to black holes. So we've talked about classical black holes. We've talked about quantum field theory. Now we want to combine them. Now, to really do this correctly, we would need a theory of quantum gravity, which is difficult. Now, depending on how these lectures go, I may or may not talk about this problem in a quantum gravity theory that we do know about, which is ADS-CFT. But for now, I'm going to be more practical. So there's a simpler way. There's a sort of first foot in the door to the problem where you don't have to go all the way to full quantum gravity. So the idea is what you do is you take a physical limit. You imagine sending G Newton to 0. So you're turning off gravitational interactions. But at the same time, you're sending the mass of the black hole. So now we're back to black holes. You're sending... you send the mass to infinity. Such that the Schwarzschild radius, Rs, which is 2 GM, is fixed. Okay. Now, if you're a stickler, you'll rightly complain that it doesn't make sense to talk about holding a dimensionful quantity fixed. So what I really mean is I'm going to be interested in experiments where the length scales are involved are of order the Schwarzschild radius. And then I'm going to take G to 0, and I'm going to keep the scale of experiments that I'm interested in of order the Schwarzschild radius as I do that. So in other words, these two things you combine into a dimensionless statement, which is that m over m Planck goes to infinity. And then this one becomes sort of length of experiments over Rs fixed. Okay, and that's the mathematical limit that I'm interested in. And this is called the quantum field theory and curved space-time limit because G is going to 0, so the gravitational coupling is gone, which means in particular that the presence of matter does not back react on the metric. Right? Einstein's equation says that some function of the metric is equal to 8 pi g times the stress energy tensor, the measure of matter. So if g is 0, then the metric is just fixed. It is what it is. So that's convenient because we can sort of ignore gravity but still talk about black holes in this limit. Maybe I should briefly comment that, so for astrophysical black holes, this is about 10 to the 38. So doing perturbation theory in 10 to the minus 38 is not a bad business to be in. Okay. So before I proceed, I'm going to have to decide whether I'm going to talk about the two-sided maximally extended Schwarzschild geometry that we talked about yesterday, or I'm going to talk about the one-sided black hole geometry that I got from collapse. Now, actually, both are interesting, and I'm going to talk about both. But it's easier to talk about the Schwarzschild, the two-sided one, first, because in the one-sided case, there's these matter shells going in. It's kind of messy. Okay, so we're going to start with the two-sided case. So to remind you, we had some Penrose diagram, which looked like that. So now remember, so this is today's first Penrose diagram. In Penrose diagrams, light moves on 45-degree angles. It represents the entire infinite space-time in one compact diagram. And at the boundaries, one of two things happens. So there's a two-sphere, which I've suppressed sitting on top of this. Its radius is a function of where you are in the diagram. And at the boundary, either the radius of the two-sphere goes to 0 or it goes to infinity. Here, it goes to 0 at the singularity here and at the singularity here. And it goes to infinity at the two spatial boundaries. Okay. Now, given that I've been drawing pictures like this all day, it shouldn't be too surprising that I'm going to try and make an analogy between this region here and the right Rindler wedge. Okay, and that's going to be the theme of the rest of the day. So let me try and be more explicit about that. Let's see. Okay, we can get rid of the get rid of the firewall now, temporarily. I think I see I have a coordinate transformation here. In my defense, it's one I wrote down yesterday. So remember in the Schwarzschild. So I'm now going to just talk about this wedge here. So we'd had these coordinates yesterday, which was the time, which sort of was slices like this, and then the radius, which was these hyperboloid slices like that. Now you can kind of see that if I zoom in over here, these slices look a lot like the boost slices that I was drawing before. Although eventually the time ones bend over and come back down as we get away from the black hole. But the story I'm going to try and sell you is that if you just look in the near horizon region of the geometry here, then it's very well approximated by Rindler space. Okay. So let me see if I can make that case a little bit more explicit. So yesterday I defined this tortoise coordinate like that. Okay. And to remind you, I'm again using my convention from yesterday that the Schwarzschild radius is 1. So that's what this is. So in these coordinates, the metric looks like this. Where, again, you implicitly can represent R in terms of R star using this equation, but I won't just because it's kind of messy. And this should look familiar, because remember in Rindler space, I wrote down some metric, which was like e to the 2 xi r times minus d tau r squared plus d xi r squared plus dy squared. Okay. So they really look pretty similar, right? I mean, it looks like maybe I have to sort of reshuffle things around a little bit, and the geometry will look the same. Now, like I said before, it's not really true because at large R, something different is going on. At R much greater than 1, something different is going on in the Schwarzschild geometry. But actually this geometry, let's see, maybe I'll do it over here. So if we look in the approximation that r star, so let me just first make one more comment. So r star equals minus infinity is the horizon, okay? So you see as r goes to 1, r star goes to minus infinity. So r star goes from minus infinity to infinity just like xi r did in Rindler space. So, and indeed for r star, you know, much less than, well, let's say minus 1. No, let's say much less than 0. I mean, it just means very negative. Okay, it's not a statement about the absolute value being small. And I still don't like that. Well, I never know how to write this. R star is large and negative. So in this limit, this metric here just becomes e to the r star minus 1 times minus dt squared plus dr star squared plus d omega squared. There's a typo in my notes. Okay. With an r squared. Okay. And now it's really starting to look. Right now we've got the exponential here. We've got the exponential there. And it seems pretty clear that if we just reshuffle things around a little bit, we can make it look exactly like this. So really the only difference actually is this 2. Okay. So to get rid of the 2, I won't even write it out. We want to define, you know, r star equals 2 times something. That puts a 4 here. And then since we want to get this combination, again, we've also got to put a 2 in t so that I get to take the 4 out. And then I really just get a constant times the Rindler metric up to one final subtlety, which is that here there's a 2-sphere and here there's a plane. So in order for this to be really true, we need to just also work in a small angular region of the sphere. We need to zoom in, you know, say it's some very small angular region where the sphere just looks like a plane. So let's see. So you know, we want to say that t is something like 2 tau r, okay? And then I guess I wrote it out here explicitly, just in case you're curious. Okay, so with this substitution, then this metric becomes identical to this one. And I can, you know, at the level of Penrose diagrams, I can make it, you know, look very clear. So here's the Schwarzschild one, and then here's the Rindler one. Okay, and there's a subtlety here I have to comment on. So previously when I did Minkowski space, I only drew half of the wedge, but that's because I had 2 spheres sitting on top in the extra piece, whereas here I have a plane sitting on top. So the plane never shrinks to 0 size, so in particular it doesn't shrink to 0 size here. So then I have to include the other half of the diamond. So then the claim is just going to be that the region here in Minkowski space has a geometry which is extremely close to the geometry here in Schwarzschild once you make these substitutions. And in particular, so that makes us strongly suspect that somebody who is in the Schwarzschild geometry hanging out at finite r star is going to see some temperature. Okay, because that's what we saw in Rindler space. We saw that in Rindler space, a constant accelerating observer, in particular one who's in this region, sees a constant temperature. And since the geometry, well, actually, it was Rindler, so we saw it here. And then in the Schwarzschild geometry, well, this part of the geometry is exactly the same. So then they must also see a temperature, with the slight subtlety that the time that's natural for the Schwarzschild observer is related with this factor of 2 to the time that's natural from the point of view of Rindler space. Okay? So what does that mean? Well, it means that for the black hole, we should see some temperature. But now instead of T Unruh, we're going to have T Hawking, which is T Unruh divided by 2. So now it's going to be 1 over 4 pi instead of 1 over 2 pi. And now just to make it a little more intuitive, I'll put the Schwarzschild radius back in. Okay.
That temperature is based on the observer falling into the black hole or outside?
Good. So whenever you talk about temperature, you're really talking about energy. And whenever you're talking about energy, you have in mind some symmetry. You haven't, because you're imagining that there's some time translation invariance you can use and then you're using the generator of that as the energy to define the temperature. So in Rindler space, the thing I used was this boost operator, okay? The thing that generates these boost translations. Now, here what I'm using is actually this T, the Schwarzschild time, which is, but the interpretation, now this T is sort of serving double duty. If you're near the horizon, this T is, it's something like the time, it's something like you have these constant accelerating guys here. But the important thing about it actually is that out near infinity, this T is just the ordinary Minkowski time. It's the time that if you're sitting far away from the black hole, the geometry just looks like Minkowski space. This T just looks like time. So then this temperature is the temperature of the black hole from the point of view of somebody sitting out at infinity. Okay. Now, let me think of how to say this. So now in order to make what I said really correct, I have to say more about the quantum state. Because one sec. Because obviously in the Rindler case, I picked the vacuum state here, and then we saw that in that state, it looks thermal for this guy. Okay. Now in the black hole, I didn't tell you what the state was, but I just said, well, if it's like this state, then it shouldn't be that different. And actually, that's sort of roughly the idea. So you imagine some slice here, and then you define a state on this slice in a number of ways. Actually, my favorite way is, again, to define it with a Euclidean path integral. But I'm not going to try and go through that again, because I know it's already unfamiliar. But the state, the Euclidean construction of the state here gives you, again, something which in this region reduces to the construction that we did before. And that state is called the Harlow-Hawking vacuum, okay, after its inventors.
Temperature outside at infinity.
Yeah.
Will be different from somebody detects temperature near the side probably.
Yeah, that's true. So because remember in the Schwarzschild coordinates, the metric was like this. So yeah, you can see that the meaning of this time in terms of the proper time changes as you get closer to the horizon. So that was the gravitational redshift that I talked about yesterday. So indeed, this time, right, is clearly, it's when R is large, then this is a 1, and then T is really the time that you like. So this is really the temperature as seen from infinity.
So this state that we talked about is again for bosons? It's like oscillators, or can you do it for Frank?
Yeah, so actually, so far everything I've said is true. It's true for any fields. So one way to see that is that in the Rindler construction I did with the Euclidean path integral, I didn't have to assume anything other than that I was doing a path integral, and it could be a fermionic or a bosonic path integral. You could have both, and it would still be true that you have this entanglement between the boost eigenstates on either side. So the same construction here would work at the same level of generality. Now, the things I said about free theories, that was more specific. And I chose to study a bosonic theory, but I could have also chosen to study a fermionic theory, and I would have come to the same conclusion.
And the same temperature?
Yes, absolutely. Yeah, and you can see that in the Rindler argument, right? Because the temperature just came from this pi, right? So it should be the same. Pi is pi for any field. Yeah. Yeah.
For the previous case, we divide into left and right. New case, exactly what is it?
Yeah, so it's still left and right, right? Because we have right infinity over here and we have left infinity over here. Because remember the two-sphere never shrinks to 0 size anywhere here except at the singularities. So this is really a different set of fields than this is. And it's the entanglement between them that's responsible for the temperature that you see here. Okay?
Observer far away from the object still have 1/4 pi r as the temperature.
Yeah, good. So
you don't have any feeling of acceleration still.
that's correct. So that's the thing that's new about black holes. So in the Rindler example, you had to be accelerating to see this temperature. But because of the black hole geometry, you don't. You can just be out at infinity, coasting along in an inertial frame, and you will see temperature. So that's the miracle of the black hole geometry, is that near the horizon, the slices that look like Rindler slices, end up turning into ordinary Minkowski slices as you get out to infinity, and they do it all on their own.
So it means, even if we have a black hole at the infinity, still I can detect the black hole because I can measure the temperature.
Well, yeah, but it's hard, right? So think about a star, right? I mean, if there were a star in the next room, we would know. But if there were a star very far away, I mean, even though the temperature is the same in both cases, at some point we're not going to be able to see it anymore because the flux is just getting smaller.
Way below the constant background.
Yeah, I was going to come. Well, yeah, that's true. Yeah, the temperature is low. That's also true. Yeah.
Okay, so here you have environment between two universes, the left and the right.
Yeah.
As opposed to what we had before.
Yes.
So does it make sense that we said that these two universes don't talk to each other?
Yeah, so they don't. So I can't. Yeah. So, but that's entanglement, right? Entanglement is correlation without communication. Yeah. Yeah.
So I know you said you didn't want to talk about the Euclidean path integral for the Schwarzschild geometry, but when you do the rotation,
yeah,
you're going to hit the singularity.
Yeah. So you're actually not. That's the fun thing about it. So the Euclidean Schwarzschild geometry is completely non-singular. Yeah.
But in doing the Euclidean path integral, I mean, locally it's fine, but globally it's not, right? Because of in curve space time you can't exactly, topological consequences might be present, which locally it's fine. As long as you're near the horizon, there's no problem.
No, but it works globally, but you just have to be careful about it.
Right.
Yeah. I mean, I'm happy to discuss the Euclidean thing because it's very beautiful. I just, time is finite. Yeah. Yeah.
So here you entangle the left and right, but this is an eternal black hole. Is there a similar? What is entangled for a collapse?
Yeah. Well, you're gonna have to ask me tomorrow, I guess, because we're running out of time. But that's the next thing to talk about. Okay. Yeah. I mean, the conclusion will be roughly the same though. And so maybe I'll close actually by also putting the units back in here, so that I can feel like a real physicist. So if we put everybody back, then we get Hawking's famous formula. Okay. So again, you see that as h bar goes to 0, the temperature goes to 0, and that's the statement that classical black holes don't radiate. Okay. The C goes to infinity limit doesn't really make sense because to talk about black holes at all, we're doing general relativity, and C is finite. So you can try and take C to infinity, but then you'll get confused because they'll just lose the black hole altogether. Yeah.
Why did you use the fact that G goes to 0 and goes to infinity?
Good. So I wasn't. So far, I didn't give you a very explicit calculation. So it's hard to tell. But this calculation was based on quantum field theory. So it was based on saying that there's fields at each point on the slice. That they describe a Hilbert space which lives on this kind of slice, and that's actually only true at G equals 0. So then you're just doing quantum field theory, but you're in some more interesting geometry than flat space. And that's a good limit because we can really control everything in that limit and compute things. Yeah, we'll see later that when I try and turn on finite G, it's harder. Yeah.
So is the result exact, or is that something like a first or second order perturbation?
Yeah. So that's the sort of the comment I was making. So in the limit that G goes to 0, it's exact. Okay. But you should really interpret everything I say in this and in the beginning of the next lecture as being in a perturbative expansion in M Planck over the mass of the black hole. And I'm working to 0th order in this expansion. Yeah. Okay. So I guess probably we should call it. Yeah.
Okay, and we'll start in 11.
Yeah.